One of the weird, interesting, troubling things about AI is the ways in which its behavior forces us to reckon with a lot of the different conceptions we have about who we are, about what things mean. As we develop systems whose behavior feels harder and harder to explain, a lot of the terms we thought we once understood start to feel less helpful. But framing and debates over terms are one thing. In articulating positive futures for AI, we need to look to how we want to develop systems in the future, how we want to relate to them, how they'll impact the ways we relate to each other. My guest today, Venkatesh Rao, has been thinking deeply about a number of areas that come to bear on how we need to be thinking about AI right now. We had a wide-ranging discussion that goes into the importance of embodiment and multi-agent systems, his commitments about personhood and what it takes to have personhood, and how protocols will be very important to the future we're building. This is the Gradient Podcast. I'm Daniel Bashir. Here's where I tell you to do all the things about subscribing and following us in all the various places that you're able to follow us. Instead of filling this time with sponsorship ads, I'll just ask you again and again to leave me a rating, to share this with your friends, and anything else you'd like to do. It helps me a lot. Thanks. But now, without further ado, Venkatesh Rao. So Venkat, you've been writing for a very, very long time and probably have some of the widest range of the different guests I've had on this podcast. And I'm kind of aware of your background in aerospace engineering. I want to start with what's with I don't know, how do you get to writing Ribbon Farm? I think you've told the story in different ways, but I still kind of want to understand a little bit of what goes on inside your head as you go through that.
Yeah, it's I guess there's many ways to tell a story like that. Like anytime you try to summarize 20 years or more. But since you cover academic research and stuff, it's kind of interesting to pull on that thread. So I used to write in the beginning of grad school when I landed in Michigan in 1997 to start my grad program. And I started writing online around then, but that wasn't serious. I was just kind of dabbling. Then, in the middle of my PhD, I took a break, went and worked for an online community startup in Austin called Suleika, and I used to write there. Then I kind of quit writing online for a while, but I had a lot of random notes going on because alongside my PhD and later postdoc work, it was like anytime you're working on technical problems, sparks all sorts of non-technical thoughts because I think fundamentally I'm not one of those native techno-mathematical thinker types. Like I'm always trying to make connections between technical thinking and non-technical sort of metaphors and allegories and narratives and stuff. So I finished my PhD with I don't know, 5, 6 3-ring binders of papers and notes and things that were related to my technical stuff, but also couple of folders worth of writing drafts. Same thing with my postdoc. And at the end of my postdoc, I was like, I need an outlet to write. So blogging was kind of taking on then. So I started Ribbon Farm in 2007. And a lot of what I wrote about in the first couple of years was just piled up notes, which I would say were kind of gen pop versions of ideas I initially thought of in technical ways. So that was kind of a fun way to get started. And eventually, I guess I found my voice in the medium itself. So I was no longer translating thoughts that had started in kind of an academic mold into popular mold. I was starting to think in popular ways in a native sense. So that was kind of how it started.
When I read your writing, I do get that sense of a very distinct voice and point of view you have. And I think we'll get into this when we talk about mediocre computing and protocolization, but I do feel like there's this maybe overarching kind of set of commitments or ideas about the future, for example, how that might look that is going on, and it kind of manifests in different ways in your various essays. And one thing I'm wondering about is what it looked like for you to form that voice And I guess if this makes sense as a word to describe anything, any aspect of what you do, like the maybe theory of change aspect of your work, if that's kind of there for you at all, if you think about that.
I don't think I've ever thought explicitly in terms of voice per se, because for me, writing has never been an act of public performance. It's more like there are things I want to think about, and I tend to be an extremely long attention span type. So almost the opposite of ADHD. Like if I develop an interest at like age 14, I'm likely to have continued it for like 30, 40 years. So my interests tend to be extremely longitudinal. And as my context and the media I work in change, it's like I work on the ideas in different ways, but the ideas remain the same. And I think this is kind of what ends up coming across as a distinctive voice. A couple of examples might help make that clear. Like, I think I first got interested in time as a subject to think about sometime early in grad school, because in control theory, which I think of as like an evil twin of computer science, a big difference between control theory and computer science is the explicit element of time. Because anytime you're working on like a feedback controlled engineered artifact like a missile or a car or anything, it lives in real time. It can go unstable in real time. So time is a very ever present thing you think about whenever you're designing control systems. And when I was doing my early work in academia, I was doing like classical controls, thinking about like time domain, ordinary differential equation models of phenomena. I was very interested in complex systems, how time manifests in complex systems, how it like, chaotic systems become sensitive to initial conditions and diverge. So that's kind of one way of thinking about time. Then later in my PhD and postdoc, I got really interested in AI. This was, good old fashioned AI. And I discovered one of the ways of looking at time that has still remained seriously influential for me. This is called the temporal interval calculus. It's by Allen from 1983. I forget his first name. But the temporal interval calculus is kind of like a symbolic way of representing intervals of time. So classical planning normally uses points of time. So you have like, causal graph type structures where event A influences in event B. And it turns out that's not a good way of representing time in the real world. And the temporal interval calculus represents time in the form of durations. So small intervals of time, that's where the name comes from. And this looks much more like a Gantt chart or something, right? And if you switch for planning purposes from point-based time to interval-based time, suddenly strips planning kind of like stops working. It's way hairier. You're talking about like intervals overlapping, one interval being in another. An example you often use is there are certain doors to which to open which you need two actions happening simultaneously. You have to turn the handle and push it, right? So two actions that have a duration in time and kind of have to overlap in certain ways. It's really hard to represent that in like simpler models of timing. So this was a model I used a lot in my postdoc, and that's another way of thinking of time. Then when I started blogging, I was like, I really still like thinking about time, and there's no like easy popular way to talk about time. And I ended up taking my postdoctoral work, which was about complex planning and scheduling models in like multi-agent domains for combat theaters, and basically coming up with like a pop science version of that. So I was kind of doing like, how do battlefield commanders think when they're controlling a mission? How do you like go from like the low level control loops of like a predator drone firing a missile at a target up the kill chain, as it's called, very dark terminology in the military, all the way up to like maybe scheduling and planning abstract systems that the planners may use, low level control loops, things like that. So it was like really rich and complex. And it turned out that if I threw away most of the technical stuff, I did retain a little bit. It made for a really interesting sort of book on decision making using narratives. And when I wrote this book, one of these sort of niche audiences with which it became popular was the Marines. And the Marines use the philosophy of John Boyd. So John Boyd was one of the premier military strategists of the 20th century. Some people call him like the greatest strategist since Sun Tzu. And he's famous for a model of battlefield decision making called the OODA loop: observe, orient, decide, act. And that's a very complex adaptive control loop that talks about how streams of time get entangled in decision making. And there's a lot of like aphoristic wisdom in OODA loops. For example, you might say something like, to really defeat an enemy, you have to get inside their OODA loop. Now, this is a very esoteric, I don't know, uh, old Chinese saying kind of like statement, but if you start modeling time properly, you can sort of really get insight out of that. So this is an example of a through line in my thinking. And I think one of the things that happens when people randomly read one of my blog articles in, say, 2015, which is like 10 years after I stopped doing like academic technical work, it kind of still peeks through. It's like clear that I'm speaking from an idiom that comes from very different traditions than, typical liberal arts people. So even if I'm talking about something like, memes and culture, I think the differences in my history and the few problems I've been on for decades, it kind of comes through. So I think that's a very long-winded answer to what exactly I mean by voice. And I think I have like a few more through-line themes like this. Like I think multi-agent systems are another one. They were the topic of my PhD. They were postdoc, and I think my most famous blogging article is this series called the Gervais Principle, which is about office politics through the lens of the show The Office. But in my head, in my head canon, so to speak, I was kind of just doing adversarial multi-agent systems theory applied to human organizations as opposed to systems of robots. So in my head, there was a continuity which is perhaps missing in the reader's mind. And I think that makes for interesting surprises.
Yeah, you sent me your patch models paper from your academic work, and I'm seeing a lot of what you're saying here when it comes to through lines. So you mentioned multi-agent systems, and this is kind of there, and it's going to come back for us when we get to your essay on mass Muddler intelligence. And I think in this paper, I was also kind of seeing some other things. So you mentioned time, which of course comes across here. Another thread that was kind of interesting and that I think we like ran into each other about was the philosophy of language angle. And I noticed that some of the commentary you wrote on like representation capabilities in this paper had to do with human mental models and the kind of possible world semantics that are involved. And you were talking about how this is understood in analytical philosophy. And that felt like, I don't know, I feel like I see this maybe gestured at sometimes in AI papers, but it feels like there aren't a lot of people who go super deeply into a topic like that and then kind of try to integrate it into their domain of expertise. And I'm curious what it looked like for you to do something like that.
So I think that paper, it's my favorite paper to, I think, as a piece of academic writing. It's not stellar, but it was my favorite paper to write among the few I wrote in academia. The interesting thing about that paper is at that time I was friends with a couple of actual academic philosophers, and I kind of like interacted with them briefly about this. Um, but okay, so the paper, the problem it was working on was at that time there was what's known as a Muri grant. I think it was an Air Force grant to a multi-university research initiative. That's what Muri stands for. So there was like teams at I did this at Cornell. There was a team at I think UC Irvine maybe, and a couple of other places. And all were given the challenge of you're given a battlefield with lots of robots and human commanders and like hundreds of moving parts moving around. How do you actually run this? This was like, the context of the Iraq war and so forth. And I was I think I was like too young and naive to not know that this was an impossible problem. So I actually went at it, which is kind of hilarious. The sort of thing you will only do when you're like a young and inexperienced researcher. So I said, all right, I'm a controls guy, but this is way more complexity than a normal ordinary differential equations type control model can represent. So clearly you need an abstraction hierarchy of representations. So the first piece I picked up was this thing called the region connection calculus, so which is actually an extension of the temporal interval calculus I mentioned earlier. It does for space what the temporal interval calculus does for time. So just think of it as like polygons moving around in space and intersecting, and there's a systematic semantics of how you represent, two polygons being disconnected, touching, overlapping, one being inside the other, and so forth. And the reason I thought this was interesting is One, it's a very good way to represent situations in geography. So if you're saying something like, SEAL Team 6 is inside the terrorist compound or something like that, how do you represent that as an assertion you can reason with, right? Uh, and by the way, I like picking sort of the dark problem context because sometimes we tend to lose sight of just how much academic work is like funded by these dark problems in a way. But so yeah, so that's kind of the modeling thing going on. And the reason I picked that was a little comment I heard by, I forget his name now, Kevin, I forget his last name. He was a professor at OSU. When I was finishing my PhD and about to start my postdoc, he gave a talk. His work was on bio-inspired models of control, so swarms of fish and schools of fish and things like that. And a casual remark he made was, schools of fish can pass through each other. And for me, that was an aha moment because when you do robotics and control, you spend all your time down in the weeds of like obstacle avoidance, and very hard to come up above that abstraction because it's such a hard problem. People solve it generation after generation. Like, every generation of grad students goes at like obstacle avoidance, and I was sick of it. I was like, how are you ever supposed to get up to abstract planning and scheduling problem if all you're doing is path planning around obstacles all the time and you never go above? So I used this RCC8 representation to basically define tolerance zones around robots and said, all right, I'm just not going to do obstacle avoidance. If robot A needs to go from point A to point B and another one goes from point C to point D and they intersect and there's a chance of a collision, I'm just going to represent that as like an abstract sort of like band of tolerances, and they can kind of like just make their own way. And I'm going to assume the path planning problem is solved. So I had like a bunch of like undergrad students working with me who were solving the constrained path planning problem, saying go from point A to point B between time T1 to T2 with these tolerances. Make sure you don't hit anything. So that was a low level problem. I was using RCC8 as the abstract representation. And that gave me a model that was abstract. I could plan and schedule with it, but I didn't have to solve the detailed control theory problems of like feedback control, obstacle avoidance, things like that. And I was like, all right, now I can do planning and control. And then I ran into the problem of, if I want to model how human commanders on battlefields actually think about the situation, with if then logic of like, if the enemy attacks from that side, I'm going to flank on that other side. So there's a lot of counterfactual reasoning going on. And looking for ways to represent that, I kind of like discovered modal logic. So modal logic is a kind of second order logic. It uses two additional sort of qualifiers. So just like there's existence and universal, symbols before logical statements, there's a little diamond shaped symbol and a little square shaped symbol that represent the statements in all possible worlds or in some possible worlds. So that's this is called modal logic. It's from analytical philosophy, like a century old stuff. Unfortunately, it's like completely intractable to compute with. So if you try to do like classical GoFi style planning and scheduling with modal logic representations, you're kind of screwed. And I didn't know that going in. I got to very good representations of, all right, Commander A thinks this way, Commander B thinks this way. They're representing the game in a lot of different ways. And this is how all the reasoning works. And it turns out that the representation is like, I don't know, probably X space complete or some horrendous little intractable thing. If you can represent it at all, it's not possible to like, strips is like equivalent to first order logic. It can't do second order logic as far as I know. So, but I found that the representation itself was powerful enough that it becomes a good battlefield decision support system. And then, you can use human heuristics and things like that. So the reason I'm kind of telling you this complicated story is, the paper kind of gave me a taste of what it takes to represent all of decision making, including logic, constraints, first, second order reasoning, beliefs, desires, and intentions. So Michael Brotman at Stanford built this model called the BDI model that was very influential in both centralized and decentralized AI at the time. And you could come up with these representations of problems that would be intractable to actually solve, but the representations would still be useful. And I think I enjoyed working on that. It's kind of like the sort of thing, if I had had more experience, I wouldn't have taken on. I would have simplified it to the point where I could get more tractable results. But I think that's actually a mistake. Like, I remember when I delivered the first version of the talk about this paper, I think it was at Wright-Patterson Air Force Base, since this was an Air Force project. I sort of presented all my work, and an older researcher kind of gave me one of those snarky looks and sort of like very, very superior voice said something like, "Oh, you're trying to do very abstract planning and reasoning. Let me give you something even more abstract. Why don't you just replace all this with game theory?" And I was like, "Oh my god, this guy doesn't get it." And yeah, you often get this kind of reaction in academia where people don't want to grapple with real world complexity in all its like messy glory. They want to like simplify it to a toy problem they can solve. And I think my natural instinct is to keep it realistic even if it means that I can't solve the problem, because having the full rich idea of the problem in your mind is kind of it makes for a lifelong thing you can think about. Like I still think about the problems in that paper even today sometimes.
One of my previous guests, Preetham Nakiran, once tweeted something making fun of the way people evaluate language models, which was like, toy problem, more like systematic test of reasoning abilities, which is, I guess, an interesting way of the way we go about things right now. But the tension you're talking about between something that is a useful representation and kind of exists at some level of abstraction versus the intractability of solving it, and maybe the distance from stuff that we can really get our hands around. I feel like I found that tension manifesting in different ways. One of the recent posts you had in the Mediocre Computing series, I think, talked about this in kind of a different way, which was you kind of, I guess, self-reflecting a little bit and being like, I don't want to write stuff that is an interesting way of having a lens about AI that provokes thoughtful discussion at cocktail parties, but I want something that's going to have an impact on the way this stuff actually gets implemented, because otherwise, why does it matter? And I'm curious how you think about that specific tension, maybe kind of broadly, and if that's something that's been like there latent for you as you've written.
Yeah, I think this has been one of the most rewarding growth curves of my career. I think since I started in academia, basically doing the academic thing, which is you have a problem, you find the simplest version that you don't know how to solve, write up the first original idea solution you can, and you publish it. And I wrote lots of like quote unquote toy problem papers in my PhD and postdoc. And then when I moved to industry, I worked at Xerox in the research group 2006 to 11 or so. And I got sort of like got to know how real world engineers solve real world problems as opposed to academics solving academic problems. I was hired into the printer group, and controlling a photocopier is one of the most insanely complicated things you can do. Like no academic would ever attempt it. Like a photocopier is like six different kinds of physics processes. Like there's electrostatic charging, toner gets attracted to it, paper gets attached to it, and like it gets an imprint. The paper moves through like a very complicated paper chain. And it's like you could spend a lifetime, and many people do, just designing one small piece of this. And I realized that in industry, engineers don't care about many things that academics care deeply about for like almost the wrong reasons, but they do care about a lot of things that academics think are like irrelevant. So I'll give you an example. Like in academic control theory, we care a lot about like convergence and stability proofs. It's like, oh, can you write down the equations? Is it stable? Does it converge to whatever set point? Go to industry, talk to a control engineer in industry, and they'll be like, you've written down an ordinary differential equation linear model. Let's look at the control signal that's required to stabilize it to get your proof. Oh, look, it's the signal is actually going way out of bounds of any real world controller, because real world controller actuators like motors or hydraulic cylinders, they saturate, right? There's a limit to how much force or whatever they can output. So basically, 90% of academic control theory is wrong because it does not deal with actuator nonlinearities. And if you look for the literature on actuator nonlinearities and saturation in academia, people don't like working on it because it's an ugly problem. It's like this horrible sigmoid looking function that saturates the control signal, similar to the AI deep learning type of functions. It's a mess to work with. You can't get clean stability and convergence proof except in very rare cases. But you go to industry and you find people with the opposite bias. It's like, true stability and convergence proofs, those are like false sense of security anyway if you're not dealing with important nonlinearities. Let's actually do whatever hacky little thing actually gets the controller working with the actual nonlinearities that matter. So there's almost like different value systems at work, and the value system of industry scales and the value system of academia does not scale. By that I mean, the if the academic says I'm only going to build an experiment that I can completely verify and sort of like validate and build convergence and stability proofs about, and AI and computer science have similar biases in academia. It's like, can I provably show that there's a provably correct sort of like output of this planner? This is more, classical planner, or something like, can I prove that this model is equivalent to that model? So they're concerned about these things. And if you limit your engineering to those concerns, you will never build anything more than a toy system. Whereas if you want to build like, a Boeing 747, you want to build a starship that goes to the moon, you want to build photocopiers, you're going to have to work very differently. And I think this is the tension I was getting at, which is, in a way, the blogger or thought leader version of looking for the elegant toy problem about which you can make, elegant sounding, very intellectually pleasing statements, is the kind of game we play in the blogosphere of, ooh, here's an insightful frame of what AI is. And I was making fun of myself a little bit, like, AI is a camera, not an engine. That's a frame, right? And it's insightful. It gets you some interesting thought trails. But ultimately, if you limit yourself to just getting insightful, elegant frames of thinking, it's like building academic toy models that converge but don't scale. And if you talk to how people actually build engineered systems that scale in industry, you realize that from the academic perspective, it's very ugly, but it has its own aesthetic. There's an aesthetic to engineered real world systems that scale. So, a photocopier is a beautiful thing. A very large scale Xerox machine is amazing. It's like I don't know, it's not elegant in an academic way, but it's an amazing thing. Same thing with, since we're going to talk AI, GoFi is very elegant, but toy, it does not do much. By the time you get to like, the old IBM Deep Blue first chess machines that beat Kasparov, it starts looking very janky and ugly. By the time you get to the LLMs, it starts to look like, this is like we're just throwing lots and lots of brute force compute at extremely simple like gradient descent and back propagation schemes. And there's like a million ways of doing it, but it all kind of looks like alchemy. Like, there's no motivating theory here. People are just screwing around, tweaking, and so forth. And yes, there's like some interesting results that come out, but it's not satisfying to, say, an applied mathematician. It's mostly, if you tune these things in these very fussy ways, things work. And the larger you scale, the worse it gets. Like, you look at Andrei Karpathy doing like a GPT-2 equivalent thing as a coding project on like a single workstation class machine. Then you talk to people doing the large scale foundation models, and they're mostly worried about like, things like data movement across like entire racks of servers. And this is a very ugly problem somewhere in the CUDA swamp and all sorts of things happening at like mid to low level. And if you look at it from an academic perspective, there's a lot of ugliness and not a lot of beauty. But then you start talking to practicing engineers and you start to realize that they have a very different aesthetic in what's going on. And I think this is probably how I would characterize my overall growth curve. It's like started out with an academic aesthetic bias, and I think I'm now very strongly industrial aesthetic bias. I kind of don't like toy problem, elegant frame, convergence proof types thinking. I really like things that work at scale with a lot of messy, janky, real world engineering behind it.
That's interesting. Yeah. And I don't know if this is a real correlation that I'm noting, but when I read your blog posts, I notice you do a lot of work to set up details and different things that are going to kind of come together. Even when you are crafting some of these big pictures, it's like the work takes a little bit of time for you to get into it and set up like the bases of what we're going to get into. And I do want to talk about that camera versus engine framing in a moment. But one thing that you brought up that was really important was the scaling of industrial value systems versus academia. And that stuck out to me because another one of my recent guests, Subarao Kamampati, put this in like a pretty interesting way. And I wanted to get your thoughts on it, where he's been talking a lot about how AI is becoming what he terms an ersatz natural science. And that's pretty much precisely what you were talking about. We have these LLMs that we've just thrown massive compute. And yes, there's a little bit of principle there, but not a lot. And so we now have these systems that are doing all this stuff, and they just like exist out there in the world, and they're kind of like an organism or a model organism of their own. And now we're doing all this post hoc stuff in order to understand what the hell we've created. And another thing he said along those lines that really interested me too, though, was, and I asked him about this because I needed some clarification. He's talked about how AI seems to be straying away from being an engineering discipline. And what he meant by that, I think, had some interesting interactions with what you just said, where the industry value system is like, we're not formally proving everything. That's going to limit us extremely. But I think he's talking about how AI, relative to other engineering disciplines, has gone even a step beyond that. And I think maybe the comparison he made to clarify this was, we do have like some level of unit tests for things like models. You know, we might test their accuracy, training on a certain data set and all of this, but it's really not the same level of like vigorous testing you might expect if you're an engineer trying to build a bridge and actually have that bridge constructed. And there is a debate over there on this about like the stakes, and you know, maybe AI safetyists will have very different perspectives on this, but that was an interesting way of like framing the issue to me. And I'm curious, you know, since you also come from like a, it's overlapping given the work you did, but like a different engineering discipline, how you think about all of that.
It's interesting you bring up Kamapati, because I read a lot of his work in grad school when I was trying to learn the planning stuff. He wrote some of the seminal papers uh, on the subject. Uh, but yeah, I think I basically agree, and it's it's getting away from being a classical engineering discipline to more like uh, something that's a cross between a discovery discipline and an artisan sort of like um, I use the word alchemy already. So it's like I'm mixing my metaphors badly here, but in the camera versus engine thing, I use the metaphor of this is an instrument of discovery, not an instrument of invention. It's like, you know, the James Webb Telescope looking in infrared at an astronomical object. And this is the artisan way. So think of almost like an artisan telescope, where it's like you have a formula, you don't quite know how it works or why it works, but it seems to work. And you kind of like have recipes that maybe you trade. This reminds me of like when steel making scaled from artisan to mass industrial and metallurgy was not yet a science. The early steel industry in Britain, it was extremely artisan and kind of superstition driven, where people had like didn't quite understand the metallurgy of how to go from iron to steel with like a calibrated amount of carbon and like removing impurities. And they had things like throw an onion into the furnace. So literally there was a recipe for onion steel in like the mid 19th century. Then of course metallurgy slowly became a discipline, and got slowly scientific. But that actually gives you an idea of what, if there is a science in the future of AI, what kind of science it'll be. We are used to thinking of AI as an outgrowth of classical computer science, little bit sort of like metaphoric inspiration from neuroscience. There's some parallel influence from things like control theory and robotics, but these are all engineering disciplines where you can hold the entire model of what the system is in your head, right? Like you look at a robot, you have a kinematics model, you have like some path planning. It's complicated, but it's not impossible to hold the model in your head. But as you scale, as you get more and more complexity, first so I think there's a three-phase trajectory here. First, it's simple enough to hold in your head with like toy models, elegant solutions, convergence proofs, which are a false sense of security. Remember, I already said that the convergence are like a little bit of like a child's tale you tell yourself. Phase two is when you scale to a point where that like toy grade science breaks, And now you're in a zone that looks more like alchemy, where you're like trafficking in superstitions, making note of heuristics, swapping like recipes with other practitioners, and it's somewhere like an artisan way of doing things. Then it scales even further, and the artisan models break. But now you're in a very different kind of science, right? Like metallurgy is a very, very different kind of science than chemistry or physics, because metallurgy is about the solid state physics of materials at like macro scales with all sorts of complicated things going on. Like, I have a physicist friend who studies this at OSU, Brian Skinner. He wrote a guest post for me on Ribbonfarm on what is actually happening when you forge steel into swords. Like, you have a steel, you anneal it, you heat treat it, and you take a hammer at it and like go at it. And what happens at the atomic level when you're doing that? You have like, fields getting entangled, and the physics of it is like horribly complex. And if you've taken like intro physics in college and you've maybe written down the Schrodinger equation for one atom, you can kind of tell the difference, right? You've got like regular physics that works with like toy kind of like regime systems of like a few atoms interacting. Then you've got like somewhat more tractable physics. The limit of, I think, classical model physics is things like, semiconductors being doped, superconductors, things that are relatively pure and in extremely controlled conditions. Then you get into metallurgy, which is like extremely messy real world materials mixing together, and the flavor of the science is very different. I think AI is going to do that, and I think you can see a similar trajectory in biology, right? Or the uh, complexity stack that goes up to biology. You can talk about like simple chemical reactions. Then you have like chaotic chemical reactions that might, do replication molecules in a primordial soup. Then you start getting to biochemistry, and it becomes harder and harder to model things like, the glucose cycle or insulin regulation. Now it's starting to look like a 747 or like an extremely complicated engineered artifact. The moment you go past like things like the biochemistry of glucose or protein expression with strands of DNA, you're at the limit of complexity. This is like, superconducting in physics. Once you go past that, suddenly you're talking about like, is psychiatry a science? When you use like Prozac, there's a whole thing about like, serotonin reuptake inhibitor. So it sounds very scientific, but the underlying science of it is we kind of don't know how emotions, regulation, moods, and things like that in the brain work. But we do know that pumping certain chemicals into your bloodstream affects moods and regulates moods in a way that you can engineer with, right? Like you can do things, engineer your biology, your neurophysiology, but that doesn't mean you either understand it in the sense of fundamental physics or that it is superstition, like, onion steel, like the example I mentioned. It's kind of like it's a science at the emergent level. Like, psychiatry is an emergent science. Metallurgy is an emergent science. I think AI is becoming an emergent science where you will do things that aren't as superstitious as onion steel or, Freudian models of ego, superego. They'll maybe look more like, there are antidepressant pills you can take. So if an AI is misbehaving, like I think last week GPT-4 was like messing up and spewing random Spanish for prompts, that's how do you fix that? That sounds to me like a human having a psychotic break, and the way you fix psychotic breaks in humans is there are antipsychotic drugs that work really, really well. We kind of don't know how exactly they work. We have like some idea of like what regulation is being done, but that's what it is. It's pharmacology, right? And I think this is what's happening with AI. And I think Asimov actually saw this coming when he predicted the science of robo-psychology, right? Susan Calvin in the early Asimov robot stories, you've got all these robots walking around with positronic brains following the three laws. The three laws are like potential fields set up in this really emergent complexity brain. And Susan Calvin is a robo-psychologist who knows how to like give robots therapy to fix them when the three laws are malfunctioning. And I think that's a little of a cartoon view, but we're getting to those regimes of emergent science, I would say.
There are a lot of different analogs to what you just said, but one thing I wanted to pull out with the emergent science note is a connection between something you said and something I'm thinking about. And one thing you said that I kind of liked was that you kind of criticize the use of the word intelligence as a sort of reflection of this inability we have conceptually to climb down, I guess this is your quote, like the currently illegible abstraction hierarchy ladder that's clearly buried there. And I find that really interesting because in thinking about clambering down the ladder, a connection that arose to me also while you were just talking was I've finally been reading Thomas Kuhn recently, and I think that one of the things he talks about a lot is the process of a scientific revolution as this paradigm shift when it comes to what a science views as like metaphysically basic, if I have him right. And I'm thinking about what that looks like for a field like AI. And when we talk about something as an emergent science, how that relates to the idea of scientific revolution. But what you're talking here about with intelligence in particular, I see as also like a frame shift, I guess, in what is like the basic thing we deal with. Do we deal with the units of intelligence? Well, now we're pretty clear there's something else a little bit different there, and maybe we need to clamber down the ladder a bit more. And I'm wondering if that's at all, like a sketch that stuck out to you as well.
Yeah, I think there's a few different things going on here. There are competing historical traditions. There's a culture war, and then there's basic philosophical hygiene. So let's take those three things in order. Historical tradition, like introspecting about what intelligence and the brain are, is relatively new in human history because we couldn't seriously look inside until like about the 16th century when people started dissecting stuff, right? Like you look at early ideas on how the mind works, Descartes and philosophers like that. Like Descartes had a theory of intelligence where he thought that consciousness lived in the pineal gland, which is like this gland somewhere in the brain. And that's the starting of the historical tradition, because before that people didn't really think intelligence was special. They would just have it as a bunch of virtues, as one among a bunch of virtues, like kindness, honesty, wisdom, all those things. Intelligence would be somewhere in there, cleverness, wit, whatever, right? It was just almost a linguistic descriptor. It's how you would describe a literary character if you were writing a play in the 4th century maybe. Starting in the 16th century or so, we start to take the brain seriously as a machine. We apply a machine metaphor to it, and later, as more and more technology comes in, we have this tendency to see our brains reflected in the mirror of whatever technology there is, right? And I think I would say around the time Darwin published his theories, Spencer wrote this thing. Herbert Spencer wrote this essay called "The Social Organism," which mapped kind of human society to a biological organism. And that's, I think, when people started taking the complexity of the brain truly seriously, as in, this is so complex, we should think of it as a city, right? Lots and lots of moving parts. They didn't realize just how many. They didn't realize there were 100,000 neurons back then, but still, they were starting to calibrate correctly. And that's one historical tradition that I think is important, which is the human body. I think I don't make a strong distinction between brain and body or mind and body. I'm a very strong embodiment theorist. I think embodied intelligence is key. But mapping body to complex systems like cities, societies, weather, the economy, that's one historical tradition where you look at simply the sheer number of moving parts and say, this is like the weather. We really should not think of the brain and thinking as like simple linear reductive models. We should think of, for example, stormy weather, calm weather. That's how we should think of the brain. And that's one historical tradition. The other is, honestly, bureaucracy. German and British colonial era kingdoms sort of took notes from the Chinese bureaucracy in the 18th century, set up complex bureaucracies. They needed to characterize the efficient functioning of those bureaucracies. They started doing standardized testing to staff those bureaucracies. And that was the birth of what we now call the IQ test, right? And it took a century of evolution, but by the time it became the Stanford Binet test, it had become kind of like a recruitment tool, really. It was like, all right, there's all these really complex beings walking around, hundreds of millions of them, each of them inside their skulls. There's the equivalent of a weather system or an entire economy of complexity going on. But what we really need to do is check if they're fit to fill a role filing paperwork in a bureaucracy. And how do we test that? And you come up with a test, come up with a reductive measure. You way overload it and start correlating it with all sorts of things. You come up with this sort of like little statistical artifact called G, which you then decide is some measure of generality of intelligence, then you build a whole theology on top of what's essentially a personality test that's no better than Myers-Briggs. And then you have this entire historical tradition that I think is basically um, overblown psychometrics that grew out of like a recruitment test. And the reason I'm contrasting these two things is there's fundamentally an impedance mismatch between thinking about intelligence and thinking of it in terms of like very simple measures. And look at even the semantic Morton Bailey sort of like, bait and switch maneuver that happens here, where if you agree that there is something called a G factor that gets at correlations between spatial, verbal, and mathematical reasoning, maybe, and maybe it correlates to like a real world success in some ways in a very messy and hard to deconflict way, because there's things like the Flynn effect and all these other confounding factors. But maybe you admit there's some sort of vague generality. There is this move from generality in a relative sense of we are not as specialized as insects, and then generality in the sense of like omnipotent, omniscient, godlike capabilities. And I think there's something very dangerous that happens there, which is you start thinking of the word general in completely unhinged ways. It's like, all right, when I think I'm a general intelligence, I mean that very specifically as I'm more intelligent, more generally intelligent than an ant. An ant follows pheromone trails. It goes and picks up a bit of sugar and takes it back to its anthill. I'm more general than that. I'm more adaptable. There's like theories of biological evolution that quantify that generality. There's this theory called variability selection theory that says that humans develop general cognition. I think it's by a guy named Potts, but it says that human brains have fairly general capabilities because we moved around so much and adapted to so many different environments. And you can say that we are general, more general than insects, but so are cats and dogs, and so are pigeons that have adapted to lots of environments, and they're all kind of more general than ants in different ways. So generality does not mean universality, and I think we've gone down this path of like saying, oh, generality is a relative term that we then take into absolute terms, and then we sort of conflate it with unrelated mathematical constructs like universal Turing computation. This is one of the most bad faith moves I find, right? Almost any damn thing is Turing complete. Like there's this notion of a Turing carpet, which says that almost everything is Turing complete, but it's not very useful. Like a Turing carpet is defined as a system where everything is possible, but nothing is easy, right? Like, Minecraft, Magic the Gathering, even Excel with a little bit of Visual Basic, all these things.
PowerPoint.
Yeah, just because it's universal doesn't mean it's usefully general, but we tend to make this conflation. But okay, so I think this has set up, I think, what's become the primary culture war of our time, which is you've got this philosophical tradition that respects and calibrates appropriately to the complexity of the system, that it's like, weather systems or the economy or something. And then you've got this system that is basically an overblown personality test invented by 19th century bureaucracies. And then you kind of like do a bait and switch and recode general to mean something it does not. And then you come up with, honestly, what I think of as like bullshit theories of AGI and superintelligence and alignment. That entire philosophy of way of doing AI, honestly, I think is bullshit. But what does it mean to take AI seriously down this, more complex systems modeling approach, where you say, all right, maybe it's like the market, maybe it's like a complex society. If intelligence is that kind of thing, how should we think about it? And this is where I think going down the abstraction hierarchy is very interesting, where you start with something like, all right, I can read a passage of text and draw conclusions from it, and so can GPT-4. But clearly we are doing it in very different ways. I have like, this neural hardware with cortical columns that are like wired up in some ways. GPT uses transformers with like attention mechanisms. And it's like the mechanics are very different, but somehow they're landing on very similar behaviors. It's like, at some level, we've come across this weird coincidence of two extremely different scaled up complex systems producing eerily similar behaviors now. This is a kind of generality I'm interested in. It's like, just to make it much more sort of dramatic, it is as if you have like a storm system, a hurricane over the Atlantic, and you've got the market going through like a turmoil and like stocks crashing and booming and stuff like that. And you write up a little description of a problem, like, I don't know, draw a picture of a cat and you throw it into a hurricane on one side and you throw it into the stock market at the other, and both come back to you with pictures of cats. That's the level of weird serendipitous coincidence we are getting at, which is clearly whatever it is that large models are doing and whatever it is human brains are doing, there is something more that's like agnostic to the specific mechanics of how transformer models work versus how neural models work. And that's some sort of like generality, but it is not a generality of intelligence. I think it's generality in the sense of data, as in somewhere deep inside the training data that's going into both human brains starting at birth and into large models as they're being trained, there is way more data about what cats are than we legibly process or think about or reason with, right? Like we are used to thinking and reasoning about what cats are in very narrow ways. And GoFi systems also are used to thinking about what cats are in very narrow ways. But deep learning systems somehow get in the mass of data about cats that's online, somehow they're able to extract the gestalt of catness and do very general things with cats that are very similar to how we can do very general things with the idea of cats. Maybe we can't do photorealistic representation and generate those things, but by the way, even that humans can. Like you take certain kind of extreme autistic people with severe problems in some areas of cognition, they are able to draw in photorealistic ways. I don't know if you've ever seen examples of this, but there are like people who are like seriously disabled in normal high functioning senses, but they have eidetic memories and they can like do photorealistic drawing and painting of like extremely complex scenes, right? So this tells you that at some low level of visual cortex processing, we can actually do the kind of like image generation modern AI stand, right? So something extremely beautiful and general is going on here. Uh, so yeah, that's how I think about descending the ladder of hierarchy. It's like ignore the wrong side of the historical tradition that's like overly fixated on like the psychometric way of thinking of intelligence, focus on the complex system side, bring it up to modern culture wars and ignore like the super intelligence AGI alignment. I honestly think of it as bullshit. Maybe you don't agree with me, but it's a long running argument I've had with several people. But think of it as complex systems and then ask what's happening at the data level that allows these very different complex systems with like billions of moving parts to exhibit similar behavior. And I think this sort of leads into my camera not an engine metaphor, because one way to like answer the complex question of like why are these very different abstraction hierarchies down very different technical details producing the same results, it's like if you point a really advanced reflector telescope and a really advanced refractor telescope at Jupiter or Saturn, you're going to see the same picture, right? The optical chain is very different, the image processing chain is very different, it's a mirror instead of a lens. But fundamentally, the commonality in structure you're seeing is out there in the data, not in how you're like processing it. And so long as they're doing comparable things, comparable transformations, a reflector and a refractor telescope are going to generate equivalent things. Now, one may scale differently, and this is a useful way to think about AI safety, right? Refractor telescopes are limited by optical purity of glass, how heavy a lens can get. Like the larger the lens is, the thicker it has to be in the middle. So if it's in Earth based gravity, there's a scale limit. I think the largest refractor telescope ever built was about 40. I'm an amateur astronomer, one of my hobbies, but the largest refractor telescope is about 60 inches. And the largest reflector single mirror reflector telescopes, I think, are at 10 meters. So like way like almost an order of magnitude higher. And if you do interferometric imaging telescopes, so distributed large arrays of reflector telescopes that are aligned by laser interferometry, you can get mirrors that are effectively miles across. This was, by the way, the problem I worked on in my PhD, scheduling for large interferometric space telescopes, right? But these are very, very different beasts if you look at them as pure engineered artifacts. A large lens, a large single lens, a large mirror that's in a single tube, hundreds of large mirrors that are then aligned via laser interferometry. All of them, you point them at Jupiter or Saturn, you'll get like increasingly high resolution pictures. And now we have telescopes in space. The Webb telescope can do infrared, the telescopes that can do X-ray. But again, because the commonalities in the data, the input output commonalities we see across these extremely diverse systems is a function of the data. It's not a function of the processing pipeline. So something like that, I think, is what's happening with AI right now. We are discovering generalities in large data sets by coming at it from different, like, quote unquote, telescope angles.
I want to pose some questions to you about that data processor relationship, but also first wanted to register an agreement with something you said earlier about the idea of like ditching psychometric notions we've had, because I think that there's so much discourse in the AI world going on right now about terms like reasoning, like grounding. I mean, I just released a podcast that was digging into a lot of these buzzwords, and it was really thoughtful. And I think these are important questions to interrogate, but I've also become very sympathetic to this view that it's there are ways in which I think that we can raise these terms to heights that become misguided in a sense. And since we can achieve very similar, I mean, you might have different views about what reasoning is. Professor Kamabati has a particular view about reasoning, and actually I think showed that for if you're interested in like robust reasoning, he was able to basically show that the LLMs he was working with in one of his papers didn't portray that. And so I'm okay saying that that is a system that doesn't appear to be reasoning. But when you like hypothetically do have that system, then yeah, I think it is interesting then to like ditch the word. Let's now talk about something that's a little bit lower down the ladder, because we've clearly shown that. I do think that for some things we're maybe not all the way there, as it goes with you talk about personhood, for instance, but I do think that's an interesting tack. That being said, the questions I wanted to raise for you about the processor data relationship are, it seems to me, I guess, a pretty like extreme on the one side view about data being the primary source of you kind of phrase it also as like intelligence being a latent property of data. And like coming from, I guess, an ML side here, it does seem to me also, and I don't know how this bears on your argument or if it does at all, but you could have like the same pile of data and then you train two different algorithms on it, and these two algorithms come away differently as an artifact of their inductive biases, and that inductive bias, right, is a property of the processor and not the data, right, because they might make different presuppositions about what the underlying structure of that data is. And that seems relevant to me. And I don't know if like my thinking here is falling prey to the theological raising of terms like generalization that you're talking about, but that seemed relevant. And if we look at also like comparing humans to LLMs, for instance, there's a clear difference in if you produce like somebody, a human who can speak at the level of a 5-year-old and an LLM who can speak at the level of a 5-year-old, there's a difference in the amount of data that they've experienced throughout their life. And that kind of makes me wonder a little bit about this picture you've painted and whether there's any interaction between what you're saying and what like, an ML person coming into this might think about on that front.
Ooh, you've raised a lot of threads. I'll have to pick and choose which ones I go down. First, let's talk about like things like is something reasoning, is uh, symbol grounding a relevant concern here, that kind of thing. I think one of the things we've learned thanks to the deep learning revolution is that a lot of things we thought of as in isolation, like take reasoning, right? We think of that in a particular abstract sense of, oh, there's like the metaphysics of causation, and we talk about like A causes B, logical statements and stuff, and we kind of don't ever stop to consider the embodiment of how those things are actually done. Now, if you think about how you do, say, provably correct reasoning or mathematical inference or computation as a human, think about what you do. we write strings of symbols on pieces of paper, right? And we learn in school certain ways of rewriting those strings of symbol to simplify them, compact them. There are legal and illegal operations. But what you actually pick up when you sort of learn the skill is a kind of rewrite pattern recognition. So the one that's most familiar to me is trigonometry. So I did like hundreds and hundreds of like basic trigonometric identities preparing for the entrance tests for college way back in the early 90s. And at some point I was like literally dreaming those identities. And you'll see this anytime you do like a constrained rule bound task like playing Tetris. Like I like to do like CAD design for fun for robotics and stuff. And if I spend like 5 hours playing with the CAD tool that night, I will dream of like CAD things going on. Now, the thing about working within rule bound domains is even though what we're doing has the mechanical effect of sort of like executing processes we then abstractly recognize as this is correct reasoning, this is correct inferencing. We are applying modus ponens here. What we're actually doing in an embodied sense is running a pattern recognizer repeatedly on lines and rewriting. And you can see like signs of this in the sort of like cosmetic elements of how we do this, right? Like when you rewrite an equation, you will often group terms for aesthetic sort of like clarity, right? Like you'll group them with symmetry. You will have like visual symmetry. You might like even like I remember when I used to do mathematical proofs in grad school, the moment I would scrawl in very untidy ways on the blackboard or paper when I was like exploring, figuring out how to like approach the proof. But the moment I figured out an intuitive line of attack that I thought would work, my handwriting would get slowly more and more precise. And the last draft of the proof that I ever wrote on paper with a few mistakes, I'd be like, this is close enough. I need to shift to LaTeX and start typesetting it in LaTeX because I need that visual feedback of like beautiful symmetry, the symbols making sense, everything. At that point, what I'm doing is a kind of like running a pattern recognizer on a visual symmetry problem. It's almost like I'm now generating images of cats. So I'm working, even though the effect of what I'm doing is mechanically verifiable proofs or whatever, what I'm actually doing is running a kind of intuitive art process. And I think this is true of a lot of other things as well. Like take we talk a lot about symbol grounding and reification and what does it mean. Like you've seen the famous painting of this is not a pipe, right? And there's like levels of direction you can have, but ultimately you're always working with an embodiment. When I'm using an extremely abstract word, like to pick one at random, the new sphere. The new sphere is like a mystical term that spiritually inclined people like to use to talk about like, the exalted realm where the soul lives and so forth, right? Like an abstraction hierarchy, 15 levels deep there. But anytime you're actually talking to somebody about such spiritual conversational matters, you're using the word new sphere, right? You're literally writing it down or typing it, right? And here's one of my biases. I think in human cognition, there is no abstraction. We are always working at a completely flat two-dimensional level. We just are very, very good at forgetting what the embodiment is. We think we are reasoning when actually what we're doing is rewriting lines of symbols on paper. We think we are doing symbol grounding abstract discussions when really what we're doing is replacing clusters of words with other words. And in a sense, we are always at one flat level of embodiment. Now, the question is, sometimes these things we then take a step back and analyze them from a different lens, right? I do this pattern recognition process and maybe generate a proof, and I give it to somebody else, and they now have the task of verifying, is this correct? Again, they're doing a kind of pattern recognition. It's like, do the dimensions match up in this physics equation? Am I adding up squared terms and coming up with a squared term, or am I mixing up my exponents? They're doing very basic quality control type checking. That's how proof checking actually works. And I think if you ask what computers do when we say they have like formal properties and do these things in like formally verifiable ways, the same thing applies to the programs, right? We write code that, like, say you write a piece of code that checks, that verifies that, I don't know, a graph is fully connected or something like that. Again, we are actually doing pattern recognition on lines of code, and we think the code is consistent if the code looks a certain way and then it passes a bunch of tests. You're never far away from an embodiment. There's never a step in this entire way of thinking, whether you're doing it as a human or using a computer to do it, where you have ever escaped from embodiment. You're always working with some embodied thing. You're working with tests that pass or not in a statistical sense. So I have this very strong belief that all computation and cognition, whether human or silicon, is strongly embodied. And I think this is a tradition that goes back to all of computer science. You've probably heard of Landauer's theorem, which basically argues that computation is physical and obeys the second law of thermodynamics, right? Deleting a bit increases entropy. So there's no such thing as computation that gets away from physical reality. And the moment you realize where your contact with reality is happening, all your ideas about, like, oh, this is formally true, start to break down. Like, do you know for a fact that Andrew Wiles' proof of Fermat's last theorem is correct? Who the hell knows? It's this huge complicated structure that's centuries of mathematics that has been socially proven by a bunch of humans that have gone through like a verification process of the sort I've talked about. So this is why I've kind of like I think I've abandoned taking non-object level abstractions seriously. I still use them, but I think of them as, it may look like I'm doing an abstract thing, but really what I'm doing is an embodied behavior of pattern recognition and generation with a different embodiment that I'm kind of like choosing to ignore, whether it's pen or paper or something, right? Um, so this is kind of like a complicated answer to your question of like, processing versus data. So I think the way I would answer your original question is, the inductive biases in a stream of processing approaching that manipulates a set of data are, the historical trajectory is, we kind of loosen up our procedural game playing and pattern recognition progressively, and more of our biases that are encoded in, like, like take strips planning versus, like, just using an RL algorithm on a robot to like just fumble around and figure out how to move something. Those are two very different paradigms. Why have we replaced this sort of like complex symbolic computation thing with this thing that's just like, a robot flailing its arms around? But they kind of like, at some point, one works better than the other. The formal thing works better than the informal thing, but you throw enough compute at it, and suddenly the RL based robot is like doing complicated planning maneuvers that the GoFi planner cannot do at all. And we do this by throwing away more and more of like our formal biases. And then what starts shining through is biases that are inherent in our own training data. And I think that's kind of what happens. It's like, as you simplify the processing stack, you're no longer trying to do first order reasoning or like planning algorithms or something. Everything is now just being thrown at a large model that's doing some sort of weights update. So you've radically simplified the processing stack, which means there's fewer biases in it, which means the more data you throw at it, the more it's the biases of the data that are shining through, right? In humans, it's the case that our foundation models are in our DNA. So our DNA is like equivalent of like foundation models. Our sort of like refinement training is kind of like our nurture. And then, you've got the same sort of analogy all over the place. So, eh, and you can kind of see this, like, I think I've mentioned this recently. It's like, there's so much in our behavior that's actually a function of our data deeply buried in our genome rather than our even living conditioning. Like, my favorite example of this is what's called the mammalian dive reflex. So the reason you feel very fresh when you step into a cold shower or you dunk your head inside the water is, mammals have this deeply evolved, all mammals have this response to being shoved underwater because they think they're going to drown and need to start swimming, which is like, lots of biochemical changes start happening, and endorphins rush through your brain. You wake up, you start using oxygen more efficiently. Where did all this come from? Where is this intelligence latent? Clearly, it's part of our genetic code that's expressed in almost purely automatic brainstem and below levels. And in a way, it's like biases in training data that are somewhere deep in our evolutionary history shared with all other mammals. So sometime, I don't know, 64 million years ago, some early mammal got dunked into water and had a mutation that said it reacted a certain way. It's that training data. It's still in us, right? So that's kind of what I mean. It's like all this formal stuff is a little bit of an illusion that we kind of, that's useful sometimes. And it's all embodied computation at some level. And as you simplify that stack of embodied computation, more and more the bias is in the data, not in the mechanics.
Another way I'm now thinking of that, given what you just said, in light of the movement towards a transformer architecture is the the success of it in different domains, which is something everybody's kind of aware of at this point, but that's the important aspect of that too is the lightening of inductive biases we've seen as we progress towards that architecture, which isn't to say that it is no inductive biases at all, because as ML people familiar with the No Free Lunch Theorem would know, like you can't have a system with no biases at all that learns and generalizes at all. But you compare it to, say, you look at the vision transformer versus a convolutional neural network, and it's making fewer presuppositions about, the structure of images and things like that.
Mhm. Yeah, like that's a very good example, right? A CNN uses like a kernel type structure, which assumes it's like a two-dimensional image and it's moving a mask all over the place. Whereas an attention mechanism is like mathematically more general. If you look at the equations, it's obvious that it's much more mathematically general. And it's interesting you bring up no free lunch theorems. David Walpert is another blast from the past from my grad school era. He was writing that stuff back then, and yeah, I went to one of the conferences he organized and presented some of the patch model stuff there. Actually, um, it's kind of funny how this is bringing up a lot. But I think the way I would react to what you just said is the only true source of formal structure in the world is math and physics, right? And quite often, a lot of our formal reasoning is really application of like really hard laws of physics that we don't know of violations of, right? Like, why is it that we've been talking about like formal representations, rule bound systems, things like that, traditional go-fi kind of stuff? Where can you actually apply that? And you look around and ask, what are the most clean-edged lawful systems out there? It has to do with things like, pure number theory or classical mechanics in outer space where there's no friction and you can build like Hamiltonian models, and it's like, classical Newtonian physics applies perfectly. I think what we are seeing in generalized intelligence is we live in this world which is mostly a mess. Most of the phenomena and circumstances we deal with, like recognizing a cat against a complicated background, it's it's a mess. It's basically a statistical problem, and you learn from a huge number of examples with like lots and lots of exceptions. And useful generalized theories are not super useful, right? Like, yes, you can come up with a formal model of a cat as like this kind of body with a spherical head, and you can come up with a very old-fashioned geometric machine vision way of like trying to detect whether a thing is a cat. It's going to perform terribly. Its hit rate is going to be like 30%, I think. um, or you can do this thing of like just train on a huge amount of data, and sometimes it'll mistake, I don't know, muffins for cats and so forth, but its accuracy rate is going to be far higher. Similar with language, right? Language is a domain where Noam Chomsky in like the 1950s came up with this model of maybe there's like a formal grammar like thing underlying the structure of all language, and you can go after language in that way, like in a classical physics way. Like maybe there's a Newton's laws of language that exists, and that's what Chomskyan sort of models of language are. And you go down that path and you hit a ceiling very quickly. It's like, formal models of language, if you use that to do natural language processing with like, universal grammar structures and trying to learn all about nouns and verbs and all that shit, don't get very far. At some point, you stall out at like natural language understanding, and then you throw away all that conceptual hierarchy, and you just say, "I'm just going to learn on a huge corpus of language, and it's going to learn all sorts of things, including the common mistakes people make, idiomatic patterns of speech, weird little twists in the English language, exceptions to every rule." And what it's doing is it's learning that language as a domain, it's maybe 30% formalizable based on like our assumption that there's some sort of universal grammar of a Chomskyan sense, but about 60 to 70% is a long tail of weird exceptions, right? And this, it's useful to throw away most theories and just learn the exceptions, because that's how you get to high performance. Actually, the same is true of physics. Like, if you want to learn weather prediction on masses of data sets, it's really, really hard. You use supercomputing and high performance computing, and you can maybe get like 1 week out with full Navier-Stokes type CFD models, or you can do like energy mass balance models and get climate models that are accurate in a different sense over the scale of centuries. But as people discovered very early in supercomputing, mid-grade weather prediction that's in between recent weather and climate is basically impossibly hard. But I think now, if you threw ML at it, modern deep learning, you could actually get somewhere. This is physics, but not in the sense of like astronomy predictions, where Newton's laws gives you like 99.999% accuracy. You can use an ordinary differential equation integrator of like 10th order Runge-Kutta or whatever, and you can predict the orbit of Jupiter a million years in the future, right? This is not that kind of physics. This is everyday physics. And everyday physics, I think, is much closer to natural language than it is to astronomical bodies. And I think this is kind of key to where we are right now, which is we are. This goes back to my point about going from like clean toy physics to emergent physics. If you wanted to deal with physics the way humans deal with it, like making a cup of tea, cooking in the kitchen, like sautéing broccoli in a pan. This was an example that a video came out of like Stanford recently, like a robot learning to do it. Are Newton's laws more useful? Or is a deep learning style RL method that says, all right, I'm going to put in some basic safety constraints so that the robot doesn't burn the kitchen down, but otherwise I'm going to just show it a whole lot of training videos or something like that, or let it fumble around and figure it out. What is the physics of sauteing? Is it closer to predicting the orbit of Jupiter a million years out, or is it closer to natural language learning in the sense of GPT? I think it's far closer to the latter. And this is, I think, this core of like the uh, illusion that we tend to get trapped in, because we have so much history and success with physics models that work 99% of the time in very rarefied domains like astrodynamics, that we don't recognize that even when we do have laws of physics at work, in the domains of practical use, we need emergent physics, which is more like natural language. So in a way, if you had to choose, I have to teach this robot the physics of making a cup of tea, and I can choose to throw one of two things away. I can either way throw away everything I know about Newtonian physics, or I can throw away everything I know about like how babies learn, like fumbling and making mistakes. Which would you throw away? 30 years ago, the answer was not obvious. You would say, of course, I would keep Newtonian physics. I don't know how to do robotics without Newtonian physics. Even though the data was obvious, the existence proof of biology was that babies learn how to manipulate objects without knowing Newtonian physics. Cats and like small primitive mammals learn to do it. So clearly, you don't need to know Newtonian physics to quote unquote do physics in the real world. But despite that existence proof, we were like attached to formal physics ways of modeling domains. And you can see this as late as like, I think in the 90s, there was a lovely paper called Prolegomena to Any Future Qualitative Physics, where the authors were arguing that AI would never do physics because it doesn't understand physics. This was in 2024, this sounds like a ridiculous argument, but the argument essentially was human physicists solve physics problems by knowing physics. And therefore, AI can never do it because AI can't do, beyond first order reasoning. It can't do differential equations, blah, blah, blah. It was a very complicated, noisy debate, but it all sounds like nonsense now, because it turns out throw enough compute at it and you can do physics the way a cat does. You can do physics the way a bird does. You don't need to know aerodynamics to fly. You don't need to know physics to jump up and play with a ball, right? Cats and birds do that. I think we're discovering this in physics. It's almost like some of our anthropocentric conceits are being like broken down, that our formal theories, which are very powerful, I mean, centuries of really sophisticated work, that they matter as much as we think they do. They kind of don't.
An interesting point of comparison that I think we didn't get to dig into was that of an LLM or another AI system achieving the same capabilities as like a baby in some domain. And kind of the clear difference there is the efficiency with which we're able to like soak up all of that information and then do something with it. And I know Francois Chollet, for instance, thinks that this is a really important difference when it comes to his definition of intelligence. And he also does think that deep learning is like a fundamentally doomed project for lots of reasons of his own. But the thing I'm interested in for you is kind of that efficiency question when it comes to, yes, we can make the LLM do stuff, but we do have to, as you've said, throw a great deal of compute at it. And yes, from the perspective of we are achieving a certain behavior that we're interested in, that technically doesn't matter, but it does seem independently important. And I'm curious how you think about it.
I think here people are missing a very basic point, which is that we had our own history of like massive amount of compute being thrown at the problem. We just call it evolutionary genetics, right? I mean, uh, how much of our behavior is genetically determined? Which can I used this metaphor before that our genes are basically our compiled foundation models, right? Like we have billions of 4 billion years, like life is almost as old as planet earth, and we have that entire like 4 billion years worth of like evolutionary history encoded in our genes. When people say things like we share 97% of our genome with chimpanzees, what is that 97%? Like, of course there's a lot of like messiness there, but this is basically a huge long training regime that lasted billions of years across, you could say, I don't know how many things have lived on the planet since life began, right? Each one of them is like a little computer doing some training, and then genetics and sexual reproduction are about mixing those learnings together and retraining. Each large extinction event kind of like resets, like, GPT is 5. We can think of each extinction event in biological history as like an upgrade to the foundation models, but our genes very compact. I don't know how much information content there is in our chromosomes. That kind of doesn't matter because it's the complete foundation model on the basis of which a lot of inference happens, including things like the mammalian dive response and stuff. Which means the comparison, for it to be fair, you have to say something like what GPT is doing is partly recapitulating our entire evolutionary history in the form that it's latent in our internet text and image corpus, because that output, remember, is an expression of our entire evolutionary history, not just our cultural history, but entire genetic history, right? Like, even take the uh, photographs we take. Like, AI is mostly trained on pictures taken by humans. How do humans see? We tend to see the world in certain ways. When you frame a photograph, you might focus on a face more than something. When you compose a landscape, you might like respect the idea of horizontal in it, right? If you threw a random camera up into the air, it is not likely to respect the horizontality of horizons. So much. And why is that? It's because we stand and walk upright. We look at the world in a certain way. We have bilateral symmetry with our eyes positioned in certain ways. And those facts of our genetic history are latent in the image corpus we've put online. So effectively, they used to say ontology recapitulates phylogeny. That's a statement in biology that are, ontogeny recapitulates phylogeny. It's not quite an accurate statement. How the human body develops from a single cell to mature human, it recapitulates our entire evolutionary history in some sense through various stages of evolution. It's a controversial theory, but I would state something like an LLM or large foundation model scale thing. In its training, it recapitulates the entire evolutionary history of humanity. So that's a big part of what it does. So you can't compare it straight up to a baby. But then you say you do some refinement training, you do some RAG, you do some all these like individual deployment sensitive things. That's kind of closer. That's when you should start comparing to a baby. You can say, all right, I've done this big model training. It's now downloaded onto one DGX box or whatever, and I'm using it to now do refinement training with like particular data sets in my factory. That's closer to what a baby is doing. So a baby is really doing refinement training, maybe. And this is even more obvious when you see uh, species that don't have a lot of neoteny, like, uh, cats can basically in a few weeks they have like the full complement of intelligence. They learn a little bit more but not much more. Humans learn for 25 years. It looks like neuroplasticity and learning happens for 25 years after we are born, but most animals, they basically know 99% of what they're going to know in like within weeks of being born.
That perspective connects to something else you talked about that's kind of related about the the effective experiential age humans have when they're kind of augmented in the right way by AI systems, and that they kind of have greater lived experience than their biological age would suggest. And you raised the example, I think, in the essay where you wrote this about Magnus Carlsen playing Viswanathan Anand in the 2013 Chess World Championships, and how like an AI, like a player like Magnus who started, or maybe from a younger age had access to AI systems, and the sorts of moves and strategies they can suggest is going to come up as a fundamentally different player that you can't compare directly to a non because they had such different training procedures, if you want to call it that. And connecting this all together, there's one thing you said about this that I wanted to raise a question about, which was you talk about the way that we can sort of inherit information like this and the way that we could perhaps get a digested summary of wisdom from our parents. And you liken this to taking like the weights from a trained model and then loading it up and then doing inference with those weights. And I feel like I'm not entirely convinced that's the right analogy. I feel like when I hear that, I liken it more to something like knowledge distillation. Like, you know, you take your bigger network and then you try to transfer its knowledge to some training procedure to a smaller network. Because I do think that like, yes, you can load, so in the example of like parental wisdom or a chess strategy, you can load like conclusions and stuff like that by just telling somebody about it. But I do think there is a real sense in which if I go along the like wisdom from parents route, like my mom would tell me things all the time as a kid, and I had like the propositional knowledge of this is true, I should do this. That did not mean that I actually applied the propositional knowledge. And I think that feels, you know, slightly different from the like loading the weights of that knowledge into me and then me just like doing inference with it. So I was kind of wondering about like your choice of analogy there.
So I think there's multiple levels of inheritance going on that you have to distinguish carefully, right? I wouldn't say weights from your parents' models are inherited through like the formal learning and conditioning you do through being raised by other humans. That happens through genetics. Like our DNA is 50% each from each of our parents. That's our biggest load of very specific weights inheritance. Our chromosomes inherited our personalities. So that's like 90% of our weights transfer is coming at that very low level encoding. That's our genes, right? The remaining 10% that's happening in informal ways. Yeah, I think actually Freud is a good way of thinking about this. There's id, ego, and superego, right? Id, I would map it to actually genetic transfer from your parents. It's how you, if your father is hot tempered, maybe you'll turn up hot tempered as well. And there's a lot of like cultural epigenetic angles to that level of weights transfer as well, metaphorically weights transfer. Then there is like super ego type training, which is like thou shalt not, 10 commandments. These are like the formal rules. This is kind of more like RLHF, I would say. It's not core training. It's like doing the RLHF to like constrain your model to behave nicely, right? And then in between, there is what I would call effective human transfer through like good teaching. That's not instruction, but more in the sense of like cultural transmission. So take like people in Vishwanathan Anand's generation learning chess. They would learn it from like chess textbooks, traditions of grandmasters, studying famous games. That's like play a lot of games, learn from like historically important games, and that'll sort of encode a certain set of like chess playing weights in you. Magnus Carlsen would have had that, but mainly would have had like early chess programs that could test you in ways no human tradition ever could. Therefore, he ended up with a very different set of weights. So think about like the three levels of weights. Both of them would have had gene transfer, so there's some predisposition to being good at games like chess. Then the mid level or top level would be something like, here are the formal rules of chess, which you just apply as like rewrite pattern recognition as legal moves, not legal moves, and like, the conventions of chess playing. Then the middle is all the training that's happening very differently for, say, Magnus Carlsen versus Vishwanathan Anand. And I think, of course, we're increasingly getting there where it's like getting your weights by playing with an AI program is effectively the same as playing against a grandmaster who's lived for several thousand years, and therefore you pick up that rich history, not from textbooks. This is actually the plot point of Ian M. Banks' Player of Games. I mean, have you read that? It's like oh yeah, it's basically this long before we had modern ML, which is there's these super intelligent sort of AIs that teach this human how to play a particular game from some planet they want to like do something in. Then he goes, and this planet has like a historical tradition of like thousands of years of playing this complicated chess-like game, and that's how their politics is run. You win the game, you become king or something. And this player comes in, he's never played the game before in his life except the last few months being trained by his computer. He wipes the floor with them. I'm revealing spoilers here. I think we'll see more and more of that with humans. But yeah, it's important not to make very naive analogies here, because there's a lot of like cultural transmission. This, by the way, speaks to a lot of the other topic. I don't know that we'll have time to get to. Protocols are, I think, how civilizations do DNA, right? Like, how do you know how to drive in traffic? How do you know how to behave in like formalized settings? There's this entire transmission mechanism that's based on like our civilization with its rules, norms, procedures, protocols that we transmit and become part of our unconscious ways of behavior. And this is, I think, why protocols of all sorts and AI are like peanut butter and jelly. Uh, all these means and modes of transmission of basically learned intelligence, to use the metaphor of weights. How are weights being propagated through generations of intelligent systems, whether it's computing systems, like in the case of like large foundation models, or human evolved knowledge? How is learning and knowledge being transmitted? I think these are the mechanisms. There's like something that looks like genetics. There's something that looks like super ego, Ten Commandments stuff. There's something that looks like reinforcement learning by actual in-field sort of like practice in deployment. There's something that looks like inherited protocols that have been tested over time to work. And I think you'll find analogies for this in both human systems and AI systems and any blend of the two.
We should bridge over to protocols in just a moment, but I guess maybe I kind of keep harping on this, but with like the way you just rephrased, I think that the Carlson Anand difference, I feel like I'm still seeing this as not like a simple process of weight loading, but still something more like the knowledge transfer. Because when you describe Carlson as, you have this, like you have him training with an AI system, and he now has this access to it being able to test him in ways no human could test him. He's still like, he's still got strategies in his head. He's still thinking through stuff. He's adjusting the way he plays in order to counter that. So he is still like training and adjusting himself in a sense. And I guess it's like, yeah, I don't know. Cause I guess like the weight transfer analogy just feels like
Yeah, I
a
wouldn't
little
put
bit less accurate to me.
yeah, I wouldn't put too much stress on that. It's a very loose metaphor. Obviously, you're not like translating actual weights from one node to the other. It's, it's more like there's input output behavior that's being picked up by another equally expressive system, right? Uh, and there's important subtleties here. Like we talked about David Walpert and his No Free Lunch Theorems. Another paper he wrote a while back, again in the 90s, was about the use of bias in training data to I forget the title of the paper, but his basic point was you can bias the training data in supervisory learning to speed up the learning of another system. This is basically teaching, right? When you learn say math from a teacher, they don't throw random problems at you. The problem sets are like focused on like developing particular skills, right? And I think AI systems can actually do extremely efficient or will learn to. I don't know if they can currently do it, but if you have like an AI based tutor, it's going to throw examples at you that maximally, I don't know, lock down the weights you need locked down without knowing the details. Now, but let me give you a different metaphor, or this is more than a metaphor. If you don't like weights transfer, uh, there is this in control theory, there is this theorem called the internal model principle. So the internal model principle says basically that a system that's controlling another system must have a representation of the control system inside itself. And control systems are dealing with very simple things. So take something like an inverted that might be too complex. A spring mass damper system, right? It oscillates. It's a basic simple harmonic oscillator. It's a second order ordinary differential equation. So the implication of the internal model theorem is the controller must also be a second order differential equation in some sense. So the weights transfer in that sense is much so. Okay, let me make this a little more clear. You have, say, something like a spring mass damper simple harmonic oscillator that's oscillating. You have a control system that is trying to control it with maybe a proportional integral derivative controller, what's known as a PID controller. It has three weights on the proportional term, the integral term, and the differential term. It represents a second order differential equation. Normally, what you would do is you would mathematically analyze the system to be controlled, in closed form derive kind of like the weights you might need for a stabilizing solution, and then hook the two up, and now you have a controlled system. There are systems called adaptive control systems, which basically do input output black box learning. It's like this thing has like a few free parameters that can load up the weights it needs to control the system. It's going to take the input output of the black box and just learn a controller that does the thing. But the key thing the internal model principle says is the order of the controller kind of has to be expressive enough to control the order of the system, right? And you can actually get a more powerful system that says, or more powerful result called universal stabilizing control, that says any linear system can be controlled by another system that has order at least twice the original plant. So it's kind of like similar to the Nyquist sampling theorem, but slightly different. But the reason I'm pointing out these different flavors, and there's a third one I'll point out, it's called the Ashby's laws of requisite variety, which says that a complex system, in order for it to be managed, the system that's modeling it must be equally expressive. Now, the point of all this is if there's almost like an impedance matching where the controlling thing has as much expressive power as the thing being controlled, they're matched in some way, same order differential equation, same number of parameters. So there's like same expressivity and richness. Then, using clever schemes of connecting one black box to the other, you can usually find a way for system B to learn system A. So this is actually a more general and abstract way of what we're like loosely calling weight transfer. And I think that's happening when one system is training another, whether a teacher training a student, an AI system training a chess player. It's like both sides of the system are equally expressive in terms of like the phenomenology they can express. And if the signals are full dimensional, so to speak, it's like, it doesn't matter if it's a simple harmonic oscillator if you're actually sitting doing nothing. It has to actually express its full range of behavior for the other system to pick it up. This is also, by the way, a formal theorem in control theory. There's a notion called persistency of excitation, which says the signal that's being output by a system has to be, in a sense, full or rich or full dimensional. So if it's like, 10th order system, the signal that it's outputting has to be excited in all its modes. And the way you usually do it is you inject noise into the system so that the output that comes out is fully rich. And then from that fully rich output system and the input, you can learn its behavior. This is similar to, generative models. You start with a noise field and then sort of like start perturbing it to get to an image, right? So the point of all this is you've got systems that are rich, you've got other equally rich systems trying to learn it, and you inject randomness into one end of the system being learned, behavior comes out, and that behavior can be modeled by the other system, even if it's like completely different in details, right? And this is, I think, one of the generalities that we're starting to see. It's like, you have transformers on one end, you have human neural wetware on the other. Somehow you can put them in a loop where they can learn from each other.
I think I see what you're getting at more clearly now. We should bridge the protocols, and I think the way that we had talked about doing this was you had this really interesting post also in your mediocre computing series about mass Muddler intelligence, and I think this brings together a lot of the themes that we've been talking about in different ways. And so I guess to give the basic ideas here so we can quickly get to protocols, you express how in this post you are not a fan of monolithic scaling, or you think it's going to like run out at some stage. And we need something that looks more like a construction of scalably composable agents. And you kind of make this distinction between like muddling and godding agents. And this kind of has to do with that differentiation between thinking that you can be smart enough to solve a problem, get to a global minimum at your first try, versus like you really need some level of experimentation in order to push past boundaries, to perform better, to do all these sorts of things. And I guess the important thing for us as a bridge here is you say we need protocols for AI in scaling towards these Muddler intelligences. And I want to talk a bit about like maybe this kind of broad vision for you, but then also like how protocols comes into the picture and why that's like an important problem for you.
Yep. So maybe it's easiest to start from the other end, which is it's an independent interest. I've been in the crypto blockchain world for a decade, and for the last year, I've been running this program called the Summer of Protocols for the Ethereum Foundation. And we're just going to run the second summer program this summer, and the call for applications will be out in a few weeks. So, one of the reasons I was excited to come on this podcast is we really want to get some AI people applying to the program. The call will be out in a couple of weeks. Go to summerprotocols.com. But yeah, so protocols more generally. So blockchains are, of course, one very advanced form of protocols that combine a lot of technologies. But think protocols very generally, everything from like two people shaking hands to rituals and ceremonies in religious settings or government procedures. Protocols like TCP/IP or radio communications, all those things are protocols, right? And protocols are basically codified patterns of behavior with which autonomous agents of some sort interact according to some rules, right? I do something, you do something in return, and maybe we transact, maybe we come to like a positive agreement or not. You can use game theory to model a lot of this. So that's kind of like the broad domain of what we're starting to call protocol studies. And obviously, the direct relevance to AI is if you use agents as the form factor for AI, then they have to talk to each other. So right now we are in the realm of like really large foundation models that everybody's kind of like relating to in very light client, heavy server, client server mode, right? There's these huge godlike models that we are starting to think are actually gods, and we're like in prompt loops with them. Now think about situations like, say, this is very banal, but you are a Fortune 100 enterprise. You have a lot of proprietary databases that have a lot of structured data, and you have like lots of like permissions and security architectures constraining who can see what when. Then you have different agents, like there's legal, there's marketing, there's external customers. You have a supply chain, all with like different sets of data that they have like mutual access rights to, and these access rights are usually governed by like protocols and contracts of various sorts. Now ask what happens if you throw AI into this and start replacing all the processing intelligence with this kind of LLM style intelligence, which is very fuzzy, intuitive, leaky. It's like squishy, right? It's not the old, good old fashioned AI, which could be put in a box and have like rules engines and old fashioned sort of like ways of controlling it. How do you squeeze this squishy stuff into this very rigid control or schemas, right? And this is not an easy problem. About 10 years ago, Netflix was running those ML challenges, and there was I forget the researcher, but that's when the exfiltration challenges started of like, given the input output behavior of AI model, what can you infer about the training data? And now, of course, this has become a whole huge subdiscipline of what is this called, inclusion testing or something. You probably know the terms better, but figuring out whether a piece of data has been used in the training of an input, or exfiltrating what a large model knows based on like very clever prompts. This is a very weird black magic technology to plug into extremely underpowered schemes of privacy and permissioning. And you kind of have to level up the game. And this is where certain very interesting things are happening in the world of protocols. So one that particularly excites me, let me back up here. Like an obvious way to put blockchains, cryptography, and AI together is kind of like just encrypt everything. This to me is the dull answer. It's like, if I don't want GPT-6 to pick up all the future essays I write, I basically encrypt them with powerful encryption, and I only give the keys to anybody I actually want reading. And this will work. It'll work because no matter how smart AI is, it's not going to break like the strongest forms of modern encryption, right? This kind of is like throwing out the baby with the bathwater. If we are like getting into this privacy regime where everybody's encrypting everything, which by the way, a lot of people are recommending you do now, it's like you're losing the power of most of the data. What I would really like to do is have control over how AI is used and not have that be, good faith guarantees by large corporations or something. And like maybe I give an AI absolutely everything that I've ever written and a lot of my private information as well, but I want to make sure my social security number and my financial data don't leak. How do I have a protocol that allows AI to do its squishy thing while preserving the privacy of things I want protected? So one promising approach is this thing called zero knowledge proof. So zero knowledge proof, for those who are not familiar with it, is it's a protocol of interaction between two agents. One of them is known as a prover, and the other is known as a verifier. And the verifier wants to know that the prover knows certain things, but the prover wants to like prove that without actually giving away the information. And a very there's a few ways to sort of like explain this, but kind of wrong way is the popular game of Where's Waldo, where you're looking at a picture and you have to find where the image of the character Waldo is. How do you prove to somebody that you've actually figured out where Waldo is in a picture? So here's one solution. You take a very large sheet of paper, cut a little window on it, position it exactly over where Waldo is. And if somebody asks you, do you know where Waldo is? You point to that window and say, look, I found Waldo. And then you take it away and take away your windowed piece of paper. So the other person now doesn't have the solution. They know you know the answer, but they can't actually infer it. Now, this is actually a misunderstanding of how zero knowledge proofs work, because this actually leaks information. But zero knowledge proofs are like a verifiable way, and here it's ironic. I was like challenging the idea of verifiability like half an hour ago. But yeah, it's a verifiable way of like knowing, of proving that you know things without actually revealing what you know. So there's like, you can read up the whole literature on that. So there's like this thriving little intersection discipline of zero knowledge machine learning. So it's a little cottage industry at the intersection of ML and blockchain protocols, where people are trying to like, put these together in like extremely strong and resistant way. Now this is interesting. It's not encrypting everything. It's creating access to data in a way where you're not like hiding it away completely, but you're not like letting parts of it leak that you don't want leak. So this is way above my pay grade in terms of understanding. It's some of the hardest, most complex cryptography that's happening. I can recommend people you should bring on to interview if you want to connect more. But I think zero knowledge cryptography is one example of how protocols and machine learning can be put together in really powerful ways. But it doesn't have to be just that. You can have you can have much more general ways of putting interesting protocols and AIs together. Like your phone, very soon, it'll be like flooded with little AI agents the way it currently is flooded with apps. And we've gone through like 20 years of being annoyed at how the apps don't interoperate properly and how they can't talk to each other well. It's only going to get worse with AI, right? Like you'll have your little Google AI app, you'll have your little Facebook AI app, you'll have 100 others, and each of them will want to like race to like fulfill your every need. You might have like what's the weather, something as simple as that, and you might have like a swarm of 50 agents trying to answer and like own that little piece of like interaction real estate. I think it would be much smarter to have like open protocols of interaction where you can like maybe start to train your society of agents in your preferences. It's like, oh, if I'm asking questions about shopping, let Alexa answer. If I'm asking questions about how to program, let Microsoft's Copilot answer. You define a set of rules that'll almost be like being a CEO of your own little company of agents, and all of them will learn the rules of how to operate in your workplace. How do you put this protocol together? There's not much privacy and security and permissions complexity here, but there's still a lot of multi-agent systems design complexity here. And you can like easily imagine like much more complex versions of this, right? Like, I don't know, you can have like huge teams of lawyers arguing a complex court case in like large class action lawsuits where there's like huge piles of discovery coming in from both ends. And you've got like AI agents like processing those piles of intelligence in adversarial ways. Like, how do you do that? Like, when I was working at Xerox 15 years ago, Xerox acquired a company called Amiki that does this kind of like large discovery mining. How do you do that when like five litigants with different sets of data have to kind of like share data in like court appointed ways, and then you kind of have to like process all the data in constrained ways? What are you allowed to know? What are you required to disregard in the legal proceeding? Lots of interesting stuff can happen in that kind of domain, I think. So in general, I think the intersection of like interesting protocols for multi-agent systems, both human and AI agents operating together on huge shared data sets that have like lots of different noisy provenance paths, lots of different permission and security architectures on them, and like rules of engagement. It's like if you're in a courthouse scheme, you have certain rules of engagement that you must respect in dealing with the data, right? If you're in like an international negotiation of over carbon credits, another set of rules of engagement comes in. So the idea of like putting these formal protocols of interaction together with large models that everybody is deploying in these swarms of social modes, it's going to be really interesting. I mean, it's already starting. I just heard the news that Microsoft has inked a deal with Mistral to use bunch. It's like now I'm starting to wonder, is the next generation of like Azure or Microsoft PCs going to come with like Mistral powered models plus OpenAI powered models, and which of them am I going to talk to if I'm doing something on my desktop, right? So fun stuff is already starting.
Microsoft had some updates a little while back about their OS, and I think they're already starting to integrate some LLM capabilities in there, which is really interesting. But the I guess like the high level picture, some of what you were just talking about, I know comes from this question that you pose about how do protocols evolve and keep up with the problems they target, and this is especially an issue in ML. And I'm seeing this manifest in different ways. And so, for example, one that's been on my mind recently because I'm interviewing this guy named Seth Lazar, and one of the things he's interested in, and that people are now doing a lot of political philosophy around, is similar to one of the questions you just raised with algorithmic intermediaries. How do you and I, how do people relate to one another? How do we use platforms? And I guess it does feel like there's also kind of a protocol lens to frame some of those questions.
Yeah, I think a good way to get at the heart of what protocols are is my buddy from the Ethereum Foundation, Josh Stark. He wrote this lovely essay called Atoms, Institutions, and Blockchains, where he identifies core property of certain systems that he calls hardness. Like, a diamond is hard. And he likens that to information and information theory. So just as like computer science and control theory and AI all are fundamentally founded on information theory at the like mathematical level, like how much information is in data, protocol studies and sciences are based on the notion of hardness. Hardness is the property of systems that allows us to make commitments to each other in the presence of uncertainty. It's like fake physics that we invent in order to make our lives more predictable and like coordination at scale more possible, right? Like if you and I say, let's get dinner, solving for let's get dinner is a very squishy problem being solved by two large wetware models, and it can get arbitrarily complex. So many restaurants to go to, blah blah blah. And it can, you ask an LLM, it'll give you a million suggestions. If I tell it like, I have these tastes and Daniel has these tastes and we have these dietary restrictions, where should we go to have lunch, it'll solve the problem in an LLM-ish way and come up with like a very messy set of suggestions. But how do you actually decide where you actually end up going to dinner? That's where a protocol comes in. At like some point, you have to land on a hard time, a hard date, a hard location, exchange phone numbers, and say we are going to coordinate and let each other know if we fail. That's hardness. So protocols are a mechanism for introducing hardness into uncertainty through artificial means. Now we use sometimes we draw on the laws of physics, right? Like diamonds are hard, therefore they make good currency. Gold in its pure form has a kind of like a purity testable hardness. That's another source of hardness. Um, Cryptocurrencies use the irreversibility of certain cryptographic computations. That's a mathematical source of hardness, right? And all contracting, all legal regimes, all kinds of like multi-agent coordination for solving coordination problems makes use of certain kinds of hardness. Calendars, clocks, diamonds, gold, cryptography, right? And I think the more AI goes from its like squishy, anything goes prompt loop modality, where it's living in kind of like soft, non-real time, a little aside from the world. And it's right now, I think AIs are almost like a consultant. Like you use a coding copilot, it's giving you suggestions, it's giving you ideas. You talk to an LLM, it's giving you ideas. It's not living in real hard time making commitments. This is something, by the way, good old fashioned AI was really good at, like thinking in terms of hard commitment landscapes. It's like define a goal in terms of Daniel and I both have to arrive at this restaurant at this time. to have dinner together, and therefore certain things have to happen in a very tightly constrained way. Now you can solve this in very intuitive, pattern recognizing way, or you can solve it through formal planning algorithms, but you have to land on a hard solution, right? And this technology of hardness is what protocols are, and I think AI people are starting to think about it. Blockchain people in a very narrow way have thought about it for 15 years now, but I think there is now kind of a need for a much larger umbrella study of like, how do you put intelligence and hardness and information theory together in a way that we can actually solve problems at scale. So this is going back to a theme I picked on like an hour ago, I guess, which is engineers solve real world problems at scale in the real world in its full messy glory. And despite all that messy glory, they make hard commitments to each other that actually work. Rockets get launched, they go to space, people get dinner together, right? So hardness actually somehow, in all this uncertainty with our very sophisticated intelligences, we are still able to like get to hard outcomes. And that's, I think, the sort of like moonshot holy grail here.
One thread in what you just said that I wanted to pick up on was this interesting idea that LLMs are not precisely existing in time the way you and I are existing in time. And one of the research artifacts that you suggested I look into that came from the previous summer of protocols did look into the temporal aspect of protocols. And it had this really interesting idea of like a spiral temporality. But even more interesting, I think, was the third thesis of this essay, which stated that protocols basically lack a future vision. They don't have this distinct imagination of the future that differs from the moment in which they emerge. And at the top level, when you talk about protocols, you also talk about how protocols are like engines of progress. And I'm thinking about the interaction between those two statements. For one, I'm also just like interested in what progress means to you, because I think that is like also a very overloaded term. But then how you think about that interaction, I would say it probably looks something like, it's kind of on the humans using protocols and interacting with protocols to take that visionless protocol and imagine a future out of it. But I'm kind of curious to hear how you've thought about that interaction.
Yeah. So here, since I ran the program, my thinking is very tangled up with all the other people. But one of the thoughts I had going into designing this program, a quote that was really influential for me, was by the philosopher A.N. Whitehead, which was that something like civilization progresses by the number of operations we can do without thinking about them. So Whitehead was talking actually about how children learn math, pen and paper math, which we were talking about before, right? At some point, you forget that you're writing things with ink on paper and that you're making these squiggly shapes, and all you see is the symbols. And then at some point, all you see is equations. And at some point, all you see is truth and falsity of statements, right? So layers and layers of cognition are basically sinking into the unconscious. And Whitehead's claim was civilization progresses by the number of operations you can sink into the unconscious. Now, this became the sort of like North Star sentiment for the whole protocols program, which is all protocols do this. They take things that are initially extremely foreground and in conscious awareness, shove them into the unconscious, put another layer on top, then shove that into the unconscious. So it's like, packing, it's like trash compacting. Layers and layers of behavior go very, very deep. And if somebody points out that, hey, when you're doing math, you're actually making squiggly ink marks on paper, it feels surreal, right? Because that's not the level of abstraction at which you think math. You think, I'm solving this quadratic equation. You don't say, I'm making squiggles that look like some other squiggles. But that's what protocols do. Now, connecting this to the idea that protocols are visionless and are kind of like the opposite of goal directed. I think this actually came up it started with Nadia Asparova's study of dangerous protocols. And then one of our other researchers, Olivia Steyart, picked up on it as like a broad cross-program theme. And the good way to illustrate that is think about traffic in a city, right? That's a protocol. It's got a bunch of like signaling systems, intersections, traffic flowing through, and we all know the rules of traffic. Well, some of us better than others. And largely we manage to drive, including now AI-driven, driverless cars, self-driving cars. And we all are interacting in a large city like LA or Seattle, and it's like all flowing all over the place. And we all know the rules. These rules at various levels have been ingrained in us since driver training. And deep down, we know we are supposed to drive on the right side of the road. We know that when it's red, we stop. When it's green, we go. all these behaviors are deep down. So in the Whitehead sense, they're operations that we can do without thinking about them. And this is like 6 levels deep. That's what traffic as a protocol is. There's a system of formal rules defined by the city. There's this large space of illegible behaviors around it. And a lot of it is like deep in our brains, but also deep in the environment, right? Huge numbers of assumptions are encoded in the environment. And I would recommend looking at Drew Austin's essay on urbanism that gets into this. But our cities are these embodied protocol systems where we don't even think about it. Like, lanes are a certain width, so trucks are designed to be a certain width. All these things kind of like unconsciously replicate. You don't even think about like respecting the protocols of urbanism. Like, if you decide you want to design an online delivery business without even thinking about it, you think about, all right, I'm going to use UPS and USPS. I'm going to deliver in certain ways that through certain times. Levels of protocols are unconscious. But if I asked you, what is the goal of traffic system protocols as a whole, there's kind of no answer. It's like, yes, it's a stack of protocols that allows lots of agents to get from point A to point B for various purposes. So the agents in individual users of the protocols have goals. It's like, I want to go from here to the restaurant by this time, and I might look at traffic maps. But the traffic system as a whole doesn't have goals. It's just centuries of like rules getting compressed through this Whitehead process of going unconscious. It goes back to Roman. I don't know how much of this is an apocryphal myth, but apparently today's road lane widths go back to the Roman era and how wide carts were back then. And that showed up in like, it influenced how wide train gauges were, it influenced how wide roads were. So this is as deep in memory as the Roman era, right? And it's hard to challenge those defaults. But it's a 3,000-year-old system with no goals. It's just 200 layers of like rules of varying degrees of formality that exist partly in the built environment and partly in our heads, all transmitted. Some of it, I don't know, maybe it's transmitted in our genes. It could be that old, right? Uh, and that's what I mean by protocols have no goals. They're visionless. Uh, but that's this was Whitehead's definition of progress as well. It's these goalless systems that seem to keep accumulating and getting smarter and smarter in an unconscious way, but they have no goals, but they represent progress. Civilization progresses by the more we do this, right? And AI, I think, is just the latest set of layers that are starting to settle. They're going to go deep. They're going to become like, soon we won't even notice AI in the environment in many ways. This is I guess something we haven't yet thought about, but it's already starting to happen. Like, Google search is early AI of the sort, and we don't think of it as AI anymore. Recommendation systems, again, early AI, we don't think of them as AI anymore. It's just you search, you expect to see relevant results ordered in a certain way. You go to a website and like search for a product, you expect to see recommendations a certain way. And quite soon, LLM powered chatbots or image generators that present images to you in certain ways, or movies that are like half generated and half scripted. You won't think of it as AI anymore. It's just like traffic, it's just in there in the background.
Yeah, it's just a different set of natural ways we would do search or something like this. The Drew Austin essay you mentioned was like really good, and one of the things one of the quotations I pulled out of it that I think was actually relevant to the tension, or not really the tension, but like the connection I mentioned was he was saying, well, a protocol's design often reflects the extrinsic value system or higher purpose that originally gave rise to it. The intrinsic operation of the protocol itself is independent of those values and frequently drifts further from them over time. And that drift is important and feels interesting for a number of reasons. And you were talking about the ways in which protocols can make things frictionless and kind of unconscious. And I'm thinking about this opposing trend that I see in some HCI circles that talks about the use of, and this is more for marking out and preventing like unintended, unwanted behavior, or getting people to do or use certain things less online, for instance, like slow algorithms and seamful interactions, I think is the phrase I heard for it. These ideas are interesting because they kind of also paint like the duality here of when it comes to crafting protocols and the ways, like the modes we have of interaction with systems. It feels like you need to think carefully about what are the implications for those like natural unconscious acts we have. And I guess another way I thought about this too was like there's a lot of discourse right now in the, I guess, CS engineering world about like the young kids who are growing up on ChatGPT and don't actually know how to debug. And I had like a personal experience of this when I did a little career panel at my old college, and we were talking a little bit about our, one of the students had asked us about how much we use LLMs in our daily job, and the other person who was speaking used it quite a bit, and I don't for various reasons. I'm still kind of old fashioned in that respect. And the student had this follow up question for me, which was like, if you don't use ChatGPT, how do you debug? And I was just like very struck by the fact that I was being asked that question at all. And it makes me wonder a little bit, like, what does, I think there's like different ways of looking at debugging as a protocol. I think one of the more interesting ones that I'd seen was this idea of kind of continuous hypothesis validation that's in the spirit of like the scientific method. And I think that's a really powerful way to think about and what somebody's doing when they debug. But yeah, I guess I'm in thinking about the interactions between this like behavior nudging, thinking about what is the end state of our, like what our behavior with protocols is going to look like, and then how that kind of works backwards into the construction of those protocols and what we make more seamless, what we make more seamful, and so on.
Yeah, so this is a theme that came up repeatedly in the program, and I think it's the key here is to appreciate the distinction between informationally closed systems, where the more you make smooth and frictionless, the more smooth and frictionless the entire system becomes, right? Like, take, for example, playing the game of tic tac toe when you're like a child. You don't yet understand the logic of the game and that it's fully solvable, and it's a simple enough game that we can completely solve it at a human scale. So it's actually still fun for you because you're still discovering nuances in the game. It's like, I start in the corner, these things happen. I start in the center, these things happen. But as you learn and eventually figure out that tic tac toe is like a solved game at human scale, it becomes boring, right? It's become too smooth and frictionless, and it's now become like a useless game. You can't play it anymore because there's no friction and conflict and anything happening, right? On the other hand, I imagine that's what chess or Go are like for chess and Go playing computers today, even though they're still complex enough that between humans, they're still interesting games. But the thing about non-closed systems of any scale, so closed systems, if you're smart enough, eventually you'll exhaust all the informational potential of them, and it'll become completely smooth and boring for you, right? It's a solvable world, so to speak. But what's the difference between even the simplest city and the most complicated Go-like program is a city is an open system. Things can change. Its rules of behavior can change. New elements can enter the boundary and leave the boundary. It can like morph in weird ways. An asteroid can hit it and suddenly you have a crisis on your hands, right? It's a fundamentally open system where anything can happen. And in an open system that's also evolving with protocols like we just talked about, like, things getting unconscious and more sophisticated, it's open and evolving, and that's what I define as generativity. It's open plus evolving, and in an open and evolving system, if some things are getting smoother and like more automatic and unconscious, that just frees up cognitive surplus and budget for complicating things in other ways and bringing in more complexity, right? Like, look at traffic, through Drew's example. Traffic protocols today are extremely smooth at some levels. Everybody drives on the correct side of the road, everybody reads traffic signals, but there are lots of frictions at other levels. Now it's like, highways are jammed, there's big construction roadblocks, there's accidents that hold up things forever. You get mad at people for like tailgating, things like that. So it's like, just as you no longer need cognitive bandwidth for dealing with the fully automated parts of the stack of protocols, you can now use it for dealing with different stacks. So if you go to like really old pre-industrial towns and villages with like mess of like horse carts and pedestrians, that would be like chaos for today, and traffic could not move very fast then. It would move at like a walking horse pace or like human walking pace at best. But now we are in one measure of progress. We can run traffic systems where the average speed is like 60 miles per hour, and we have problems that come from being at that level of traffic, right? And this is because in an open system, you smoothen some things, you free up cognitive surplus. Now new problems enter the domain. You can do more, but now you have to solve different problems at different loci, right? And the way to think about this in terms of the examples you talked about, debugging and doing math and things like that, is when I went to engineering school, I took a table of logarithms with me. Like for my high school exam, I had to learn to read. Have you ever done this? Have you ever used logarithm tables?
I haven't, but I had to do like multiplication tables in elementary school.
Okay, so, so even between us, there's a generational divide. Like we were not allowed in high school to use scientific calculators, so you could not just take the logarithm of a number or whatever. You had to like use log tables to look it up. You would literally say base 10 or base 2 and look up the log, right? And I was doing that, but I didn't know how to use a slide rule. And my dad, when I went off to engineering school, he was like, "Oh, I had to use a slide rule," and I was like, "I have no freaking idea." And I recently, my wife found a bunch of abacuses yard sale, and I have them. I've been meaning to learn how to use them. And my mother-in-law, who's Korean, she actually learned basic arithmetic on an abacus. She knows how to use the protocol of like computing with an abacus, and I don't. Right? Look at the fact that because mathematics and engineering education is an open, evolving system that gets more and more sophisticated. My dad knew how to use a slide rule, but he can't program. I know how to program, but I honestly can't do the kinds of sophisticated programming today's young people do. So it's like we're using up freed up cognitive surplus in other ways. And in a way, it's like happening both in time. Like, yes, I learned some assembler and I learned basic and C. I never got into like, functional programming, and I can't do all the complex like functional programming that people learn today. I don't use like, all these frameworks of JavaScript and so forth. And but my idea of debugging is like traditional debugging. You look at the syntax error, you go back to the code and look at it. More professional people use debuggers. Now people are using Chat GPT. It's like the stack keeps building up. And the one way I like to think about it in programming in particular is the previous generation's manual programming tool becomes the next generation's compiled target, right? He compiles to assembler. Modern framework based JavaScript thingies compile to JavaScript. JavaScript is now a compiled target, right? And it's now becoming clear that human prompt loop driven programming is now using traditional programming languages as a compiled target. And as we need to do less and less of that, that can get more and more optimized for the models to use, right? Just like today, because so few people actually program in assembler, let alone microcode, you have low level representations and intermediate representations that are actually designed to suit virtual machines and all those things that exist at that level. Low level assembly languages are no longer optimized with human assembly programmers in mind, right? I think that'll happen with AI driven programming tooling as well. Like maybe at some point, the AIs will generate code that's like some inscrutable intermediate representation that then compiles to C and assembly that's in an idiom that humans can barely parse. Like it'll still be well formed C language programs or assembly programs, but when we read it, it'll look to us like a Go game looked to Lee Sedol when he first lost in the Go tournament, right? His comments after the match were interesting. It's like the Go playing machine plays by the rules, but it generates game trajectories that I've never seen before, right? It's still with the rules of Go, but it's not in the idiom of humans playing Go. I think that's going to happen to programming as well. Like it'll look like C, but it won't be easily readable as C by human C programmers.
The compilation of knowledge analogy you made earlier was really interesting. I think Subara Kamabati said something very, very similar where he talks about compiling system 2 knowledge into system 1 knowledge. That's a bit more immediate, available for use. And another distinction that you raised that I think was kind of important too was this, like, you're freeing up this extra cognitive capacity, not just to like waste it, but you're actually going to use it for other things. And I think that's relevant because I think when you hear in a lot of circles the like, oh, the kids are throwing their code into ChatGPT and they're not thinking, maybe like if they're just using it to get assignments done, maybe. But if they're allocating that capacity and then thinking about other stuff that is like relevant and useful, then I feel like that's less of an issue. But I think there's also the like, I mean, I'm not that old, but the like, oh, we're old people who like didn't have LLMs when we learned to code, and now the kids are using all this newfangled technology, didn't go through the hard grind that we did.
And honestly, this is like a conversation that's almost like unrelated to technology. It's basic like economic evolution. Uh, and John Maynard Keynes wrote in the 1930s. What is that? Future Prospects for Grandchildren. That's his famous paper. And his point was that, yeah, if you have leisure, like economic productivity increases the amount of leisure you have, but then you always find more new things to do. And it's not like there's like a fixed amount of work to be done. As work gets automated and more efficient and productive, the freed up capacity, you use it to expand the boundary of the possible, right? If horses are if you walking is replaced by horses and horses by automobiles, hey, we invent planes, then we go to space. It's like, this is why there's a whole other theme we didn't get into, but I think intelligence is about expanding the boundary of the doable. So you constantly expand your boundary because you're an open evolving system in a fundamentally infinite world. Like, it doesn't matter how smart your computing capacities get, you can always expand the boundary of the part of the universe you're concerned with to screw it all up again. This is why I think it's important for AIs to live in real time, because the real world, you can always expand and loosen the boundary enough to complicate whatever intelligence you have. You can always make the problem more complicated even if your intelligence can't keep up. And that's kind of like the source of, in a way, all progress.
Yeah. So I realize I've kept you for like basically forever. So maybe I should ask you just one last question before we close out here, which is you talked about a couple of interesting directions for ML and protocols, but maybe just as like a final closer on that, let's say some ML person is interested in possibly getting involved with summer protocols this summer. What things would you be excited for them to start thinking about now or then?
Well, certainly, I already mentioned zero knowledge proofs and like social agents in real world settings, starting with like, virtual real world settings, like a bunch of social AI agents competing for your phone screen or phone behavior space. I think one general direction I would like to see AI research go in is put it in the real world as much as possible. And in terms of like, the way I think of AIs now is it's not just living in a parallel track to reality, it's living outside of time. Like, we already talked about how training an AI, it gets like thousands of years worth of learning in like a few months of training, but this is all kind of offline. It's not happening in real world. So if you think about like the life cycle of an AI and ask how does it spend its time, you could say it spends a few months experiencing a few thousand years worth of human equivalent time, but offline out of the real world. Then maybe it gets into the real world and then it slows down. It's like at this point, it can do some refinement training, it can do some, retrieval augmented generation, but fundamentally, the real world is evolving too fast for it to keep up. At some point, entropy will beat it. And effectively, it'll die a technical death, and it'll need to go back for a round of like, retrain the foundation models. That's kind of the phase we are in. We don't have AIs that can actually keep up with and live in real time because our real time living training routines aren't actually complex enough to live in the real world, basically. So that's kind of the large theme, I would say. Put AIs in real time. And the other thing I would say is start understanding how agents, starting with human agents, actually interact in solving coordination problems around hardness. So look at notions of hardness in legal contracting systems, and other ways like, we make firm commitments to each other, and maybe go back to the history of like old fashioned AI, belief, desire, intention architectures, all those interesting ideas, and start asking how can modern deep learning based AIs learn to make hard commitments to each other in real time in the real world. So that's kind of the broad um, sort of team here, whether you do it with robots or soft agents or in the cloud. That's, I think, there's a very rich amount of work to be done there. We are going to be like funding a few, like half a dozen teams maybe, and I would like at least one or two teams to have like an AI focus in their research. So I'm hoping to get some good applications.
Those are some fantastic directions. And yes, if you're listening to this, please, I'll be including links and everything. So please do go look at summer protocols, do apply. These are some really interesting, insightful directions, and I'm kind of excited to see what comes out of this summer. So, Venkat, thank you so much for taking the time. I also realize like we've been going for a while, so you've also been very generous with having this long conversation with me today. So, thank you.
Yeah, it was my pleasure. Totally. Like it's rare for me to get a chance to have this kind of like deep discussion going way back to my academic past. So thank you very much for the opportunity as well.
That's it. That's the whole episode. Thank you for listening. If you like this, really the best thing you can do is to leave me a review and to share this episode with someone who might find it interesting. You can also subscribe to the podcast in your favorite podcast player, and if you want to keep up to date with the latest from the Gradient to receive emails whenever we have new podcasts, newsletters, articles, then you can subscribe to us on Substack, where you'll get email notifications for everything.